Yes. Okay. So we will finish with this example, and I thought, okay, we'll move to something different with the descriptive set theory. I thought maybe I'll do some descriptive dynamics. Okay, but then we still have this example, yes, to finish. Example. This is the Lionel's example. So what was this? If you remember from last time, there is a circle. We take only rational points. So we agreed points of the form E, I, Q, Q irrational. And then, so it's a countable structure. And we put an arrow between 2 points. So there's a binary relation. The language L has the binary relation. And I think we agreed that it would be an arrow like that. And with this, we put it only if, so there was a formula last time, but so we look at 2 points. We go, so points are X and Y, and we start searching. We go counterclockwise, starting from X and meeting Y, and starting from Y and meeting X. And we measure the 2 angles. One of these 2 angles has to be strictly less than 180 degrees, than pi, because the points are rational, so you never hit exactly 180 because you never get 2 antipodal points. And then we look at which angle was less than 180 degrees, and we put an arrow in that order. So in this situation, the arrow goes from X to Y. So this is how this is what this model, we called it S of 2. This model, this structure L, this is this L structure, the L structure. I'm sorry? There's some other ones, yes, yeah, but we will not look at them. They are as interesting. Yes, but we will not, we'll just look at S2. He works out as, yeah, but okay, so L structure. I think it's a binary for there's 2 points, and then you do, yeah. Even though, yeah, okay. So this is an L structure. So what we are considering, I think we look at the expansion, right? We did look at the expansion, L star, yeah. L star was this, so contains L union, and we added 2 unary predicates, so both of them unary. And we interpreted them. So this is the language. And then we went to the structure S of 2 star with our standard notation. And this structure interpreted the two predicates as follows. So these are the 2 points E to I pi over 2, E to I 3 pi over 2. So these points are not in the structure. And P0 is interpreted, P0 star are all the points that are on the left-hand side, and P1 star are all the points in the structure that are on the right, in the right half of the circle, right? So let me maybe, okay, so P star, P0 star consists of points of the form what? E, I, Q, Q in Q, 0, sorry, pi over 2 less than Q less than 3 pi over 2. Yeah, and P1 star is EIQ. There's no algebra going on in the structure, so it's a little, it looks like overkill, but okay. such that what? Q and I should have written like this, right? Minus pi over 2. Yeah. Because this is the same as if I have it right. Yeah. Okay, so these are these two interpretations. So it's L star. And then we agreed. So both, this is easy to see, S2 and S2 star are Freise. So we just work with the structure, right? Freise. So so we specified the structures, and then because of it, we have their ages. And we have age. We have these two ages. And so this one, every structure here expands a structure here. This is Freise. They are Freise, so meaning ultra homogeneous. And I will leave it to you to. Did I state that? I stated this last time, yes, for people who are here. So it's easy to see because essentially, I mean, what I will leave it to you to check. This is if you have finite configurations and you move this finite configuration, then you extend. Essentially, it's the same back and forth argument as for Q. Yeah. So this is. I will not check these most of these things. Okay. Then what? Then we see that S of 2 star is a pre-compact. This is obvious. Expansion of S of 2 because you are just expanding by a finite number of predicates. So that's pre-compact. Each finite structure here has only finitely many expansions here, just because there's finitely many. The choice is finite. So that's obvious. What else is obvious? Structures in S of 2 star are rigid. Yes, because the reason is if I have a structure with these predicates, interpret they have a structure, some points come from here, some points come from here. So if you have an automorphism of this finite structure, the points that are in P1 have to stay in P1. The points that are in P0 have to stay in P0. And then, but once I have this, say, a 3-element set here and an automorphism that move it, notice that there is a linear order on that set, actually, on this part of the structure. And then it's rigid. I cannot move the elements at all. Same here. So we are done. Yes, and we also mentioned that structures here are not rigid, right? You can imagine a square will be not exactly a square, it's somewhat deformed, and you just move it by a deformed 90-degree. Okay, but here they are rigid, so it's all good. Then
Slavik, can I interrupt for a moment? The way you've defined P0 star and P1 star, they don't seem to cover the entire structure because rational number is not between minus pi over 2 and 3 pi over 2. E to IQ won't be in either of those.
Wait a second. So if I go from Q, this is where Q is 0. And then I go up to here, pi over 2, and up to here by moving Q to the negative pi over 2. So I cover the right-hand side.
That's the problem. What if, for instance, you look at the point E to the I 17?
Yes.
That doesn't.
Oh, I see what you mean. Yes. Ah, there, a good point. Okay, thanks, Andreas. Yes. So I shouldn't have tried using formulas here, I guess. This is yeah, okay, thanks. So this is S of 2 intersection right-hand side. So right side, right half. and this is S of 2 intersection. Oh, that's still wrong. Left half, right half. And so I should have written SO2 intersection this set. Okay, let me not write. Thanks. So it's this would be SO2 intersection, the set with the formulas that I had there, except that Q is not in Q. It's just arbitrary real. All right. So, okay, so these things are rigid. What else? So I won't check these things, but S of 2 star has, or age of it, in, I should have written here age, yes, or age, let me write it to be age of S2 star has the expansion property with respect to S of 2. So let's look at it roughly. Why would that be the case? Roughly speaking, if you have, so what do you have to check? You have some structure A star in age S of 2 star. So it has some points, so it's a finite structure, some points on the left, some points on the right. And then you need to manufacture for it a structure B in age of S of 2, such that no matter how you expand B to a structure in age of S of 2 star, this will embed in the expansion. So such that for each B star in age of S2 star, an expansion of B, I can embed A star. So I think we wrote it this way, into B star. So these B stars will always take them of the same kind, no matter what A is thrown at us. What we'll do is we will look at B, say more or less equally spaced rational points on the circle that are dense enough. So B more or less equally spaced rational points in S of 2, more or less equally spaced rational points in S of 2 that are dense enough. The point is that this is actually quite, so this is just B in SO2. I don't have, if I drew it this way, but you can expand B in many ways to a structure in S of 2 star, right? It doesn't have to be this. But notice that there is not that many choices how I can expand B to a structure in S of 2 star. The reason is I have all these arrows that I need to, that tell me roughly the angles between these 2 points. Between any two, they tell me that angles are less than 180 degrees. So notice as I go from here, there is a point. So let's say it has even number of points, an even number of points. There will be arrows pointing up to that point, and then when I cross, the arrow will go in the other direction. So it's now easy to see that if I put an expansion, I don't have to do it this way, but I will have to do it. I will have to put half the points on one side, half the points on the other side. I can do it in many directions, but that's what I will have to do because of the arrows remembers where the half is. Okay, so no matter how I expanded, the structure is half in P0, half in P1, and now with A star has some number of points on the left-hand side, some number of points on the right-hand side. If this fellow is dense enough, I can assume that You see, because it's half and half, by taking a rotation, I can assume they actually divided it this way. My A has some number of points here, some number of points here. And then from A, with this finite number of points in A, there will be, because of density. So this is equally spaced, makes these divisions rigid. Now, what about the dense enough? I have some number of points in A star here, some number of points in A star here. If B is dense enough, for every point in A will have a very close neighbor to it. And I can make B so dense that between every 2 points in A star, there will be many points in B. So every point in A will have a neighbor, and no neighbor will be a neighbor. No point in B will be a neighbor of 2 points in A star, right? Because I have 2 points in A star, many points in B, many points in B. This point picks something here. This one picks something here. And now I will distort A into B. I will slide it. I will map every element of A to its neighbor. And B, I make B so dense that if I look at angles between points in A star, there's finitely many of these angles. Some of these angles may be pretty close to 180 degrees. So if I move it a little bit, it may go above 180 degrees, and it will change the resulting structure will not be isomorphic to A star. But I make B so dense that these tiny movements will never go above 180 degrees if the angle was below 180 degrees. Yes. So this is the dense enough. So I can slide. I have this A star. I have the division of B, and then I can slide A star into B in such a way that the image of the slide is isomorphic to A star. So I embedded A star into B, right? So this is how you prove that. Yeah. So I will leave it to it. It would take but I hope these two properties, right? It's clear to people that these two properties will suffice to do that.
Not so much that you need to be close to a point in A. It's more that you want to be like the dense enough is given by whatever the gap is between like the largest angle you see in A.
Yes. That's correct. So yes, I would look at every angle that A gives me. Look how close it is to 180. Take that number, and then maybe divide by 2, or minus epsilon, and then that's right. That's correct.
I guess you also need to be close to everything. You do both.
I mean, another thing is I should not slide. If I have A star, a point in A star on the left-hand side of the circle, I don't want to move it to the right-hand side of the circle. That's another thing. So I want a point here. So so maybe there's two things. Another thing is how far A star is to the boundary of the division, and take that number. So take the 2, subtract epsilon, and take minimum from both of them. And I think this will. And then I need enough of them, so the slide that I do is 1-to-1. So I need if I do the slide, I need a point between every 2 points in A star. I need a point in B. So there's another number. So I think that's all. I think now we arrived at everything. So there are these 3 requirements, and I take minimum of all of them and minus epsilon. Yes, it's all work because it's final. Yep. Okay, so this has an expansion property with respect to S or S2, and then I will just write. And I will say nothing now about this, but H S of 2 star has the Ramsey property. So I will say a little bit. I will not prove it, but I will say a little bit what kind of. I mean, it looks a little exotic. This. S2 star, a little exotic, but I was connected with something familiar, and then I will leave it at that. I will not actually prove it. It's okay. So this has the Ramsey property. So we found So now we know that H star, so now we know from these properties and the theorem, we know that the universal minimal flow of odd S of 2, of odd S of 2 is this X star, is X star, where X star now there is 2, so this is, you call it G, so this is this closure of P0 star, P1 star of this in this space, of, so how do we write it? So this is, how was it? This where maybe I'll just write it this way, P0 star, P1 star. And the closure is taken in the space that we called P star. I realized the space was, it was a space of this funny space with supremum metric of all possible. In this case, we'll just take two Cantor sets because the predicates are unary, so it's a product of two Cantor sets. So it's and then we take all the product of two Cantor sets, and then metric is maximum there. It doesn't matter because it's just two Cantor sets, not infinitely many. And then I take this P0 star and P1 star and take the closure. So that's the, so this is essentially, odd moves this stuff, moves this half and that half on the circle, and then you take limits of, you know, what of these two halves as you vary elements of the odd. And then Lionel also has, so again, this will be an exercise, has a nice, so this is kind of, this is concrete enough, fine, nice, but Lionel in the paper has a still nicer representation of this X star. So a space, a G space homeomorphic to X star, through a homomorphic, a compact space on which G acts, such that there is a homeomorphism with X star that is equivariant. And so let me just draw another representation of, let me write it M of G, right? So this is universal minimal flow. We called it M of G, of M of G. So what you do this. So I'll again just draw this, and then I'll leave it to you to check that there is a homeomorphism and so forth. So what you do here, you have this underlying set of SO2. So these rational points, let's call it S. So you have this the rational points S here. And then you also consider minus S, so you consider negative S. So these are all the points that are antipodal to points in S. There's no, these two sets don't intersect, right? Because of the rationality. Okay, so you have this, and then at every point in S you take, and also S minus 1. So you really consider S union minus S, and for every point in that set. So this is a point on the circle, you form 2 points, one on the left, one on the right. Right, so you split this point, these countably many points in this way. This is okay, and then you introduce a topology on it. This is what you would expect. This is a Cantor set. I mean, if you split densely many points on the circle, you'll get a Cantor set, and you introduce circular order topology, yes? So you will get, say, these 2 points. This interval here is an open set, but you don't have to split. You have you can have an irrational point, and this is again, this interval will be an open set. So you do that, and then automorphism group acts naturally on that space. And this is X star. This is homeomorphic to X star. So split each point of S union negative S into two points. left point. So this is, you have 2 points. The left one is on the going counterclockwise from left point and right point. Yes, and then take the whole circle. You take the irrational points, all the irrational points, and then the space is all irrational points union all the split points. Yeah. So all the pairs, so these points disappear, right? Such point becomes 2, and then put the topology natural circular order topology. And natural action of S of 2. And then there is, I will leave it as for you to figure out, there is an argument that these 2 spaces are actually homeomorphic through a homeomorphism that is equivariant. Okay, and then I want to talk a little bit about, so why this example, so all these examples that we had 2 examples, and there is more. If you look at, say, Kekris Pestow-Todorczewicz paper, that when you go from a structure like here, this what we called F to F star, you add a linear order, and you add a linear order, and then here we didn't do it, so that's one thing. And notice that in the proofs, linear order shows up naturally. In the proofs, when we're doing KPT correspondence, the linear order there was a linear order that is preserved by OT of F star. It was by extreme amenability of OT of F star. So a linear order shows up naturally, and usually we extend by that linear order and get a nice situation. But here we didn't extend by a linear order. So where is that linear order, and why didn't we take it? So the reason is this. So first, that you cannot do it. So you cannot expand this S2 by a linear order, and so that X star defined with the linear order instead of these two P0 and P1 gives you the universal minimal flow. So there is no expansion of S2 by a linear order so that expansion, I should maybe expansion, maybe let's S2, let's make it S2 plus, right, to distinguish with S2 star by a linear order so that X, I will write it X plus. This is the X star defined for the expansion S2 plus is the universal minimal flow. Yep. So, yep. So, okay, so this is the same as saying, no expansion. So notice, if I add a linear order, I automatically get all structures here rigid. I automatically get pre-compactness because I expanded only by one relation symbol. What I'm missing is the expansion property and the Ramsey property. So no expansion of S of 2 by a linear order has the Ramsey property and the expansion property. Yeah. Because we know by our theorem that, okay, in that context, when rigidity is for free, rigidity and precompactness is for free, these two properties would be equivalent to this being the universal minimal flow. So one of them fails most of the time. I guess both will fail. So there is no. Well, and why is that? So let's see. So the reason for it, I guess, a simple way to see it is as follows. So from the proof last time, so do people understand what I'm saying? X plus, I just change star, right? So X plus will consist, there will be a Cantor set 2 to the n squared, right? Because I will need binary relations. And then in that, there is a natural action of G on that Cantor set. And then in that Cantor set, I will take a point. If I had an expansion, the point would be the linear order that I expanded it by. And I take the orbit of that linear order and its closure. That would be X plus. Yeah, okay. So why not? The reason is, if this were the case from last time, this is from the proof last time, that if a space like this is the universal minimal flow, then every structure in if this were the case, if X plus was a universal minimal flow of S of 2, then each structure in H S of 2 would have a finite Ramsey degree, less than or equal to the number of expansions of the structure to a structure in H of S star. The number of expansions, non-isomorphic expansions of every structure A, expansions of A to H or in H S of 2 plus. Yeah, this was in the proof. We used, I mean, all the assumptions here are fulfilled that we used in the proof. Rigidity, precompactness. This comes, notice precompactness is important here because every finite, I mean, I guess if it's not precompact, this statement is also true, but it's then for trivial reasons. I need only finitely many such expansions. Yeah. So here that's the case because there is only one relation we are adding. So there's only finitely many expansions, and then so this is a meaningful bound on the Ramsey degree. All right, but this is a problem because now what we have is take just a point. Let A be just, I will write it like this, a single point. And then how many linear orders are on a point? Can I put on a point? 1, 2 isomorphism. So then A has 1 expansion in S2 plus, no matter what I did. So it's Ramsey. So A is Ramsey. So A is Ramsey. So a point is a Ramsey point in H S of 2. So we forgot about now plus. Now this we can check fails, but this fails. This fails. So why does it fail? You just take a triangle. So it would have Ramsey degree 1. So for this A, no matter what B I take, if I color all the singletons of my structure into 2 colors, there will be a copy of B whose all points get a single color. Okay, so take B to be this structure. It's a substructure. This clearly is an H S of 2. S of 2. And I mean, I will use now this P0 and P1. I've now forget that I had them. I will use them to color points. So color, so this is the B. For that A, this is the B for which Ramsey will fail. Okay, so now color S of 2 by 0, or by if color points of by 0 if the point is in the left half, the column is in the left half, and 1 if the point is in the right half. That's your coloring. And now notice that this B, it's impossible for all the points to be on one side, because then one of the arrows would be reversed. Because all 3, is that clear, right? If they were all on 3 points on one side, the arrows go like this. So you don't get a cycle like that. So it has to, and also on the left-hand side. So it has to have points on the left and on the right, but this means it's not monochromatic. So notice. So this is kind of this rigidity, somewhat rigid. So rigid. So note, no copy of B in S of 2 has all points, all its points on the left side, and no copy has all points, all its points on the right side. So it is not monochromatic. Points, so you have points of both colors. All right. So this cannot, so we cannot use a linear order here. All right. But now you can ask, where is this linear? There was a linear order in the theorem. It showed up as a, if you remember. So okay. So what is this linear order? And this is connected with this Ramsey that I will leave it to you to check. So as I said, this is kind of an exotic situation, but because we'll find this linear order, the Ramsey for this age will translate to a Ramsey for enriched linear orders, let's put it this way, and then this is something you can find in the literature. Okay, so where is this linear order? Well, it's kind of showed up already here with minus S. So what you do is this, that you have this, your structure. This is S of 2. And then what you do, you leave the left side alone. So this is just, this part is just P0 star, yes? You leave it alone. And every point in P1 star, you transfer to the antipodal point on the left-hand side. Yeah. So here you look union minus P1 star. And you put, now everybody is on the left side, and there is a linear order here. So you put the linear order here. So put make into a linear order in the natural way, according to the y coordinate. According to the y coordinate. So that's the linear order. And then you, of course, you want the linear order on S2, so you just pull it back to, so there is a bijection from S2 to here, and then you pull back the linear order to S of 2, and then, okay, maybe I should say it, and then pull it back to S of 2. Yes, so what will happen here, what really happens is, on this side, the linear order is whatever you, actually, according, on P0 star, the linear order is what it was according to the y coordinate. On P1 star itself, it's reversed, right? So it's a linear order according to y coordinate, but reversed. And then you have to say, how do I compare 2 points from P1 and P2? And this is, okay. So, I mean, this gives you, but I think it's, if you just do an arrow like that, if the arrow goes in this direction, then you put that point below that point. So if you have a point, let's see, what would you have? Say a point here and a point here, and there is an arrow in that direction, this will be above. Yes, this will be above because it will be here. So it's then if the 2 points come from 2 different halves, so there is one point from P0, 1 point from P1. You look up where the arrow is pointing, and this point is above. So this is, you can reformulate it in this way. Okay, and that linear order, this linear order is fixed. This linear order is fixed by the automorphism group of S2 star. This linear order is fixed with by S of 2 star. That's the extremely amenable group. This is an extremely amenable group because of Ramsey property and all that. And so there will be a linear order. It fixes. It will. That's the linear order. Yeah. So it does show up here. Yeah, the linear order. But you cannot. This is not an appropriate expansion because it doesn't give you the right. Okay. So this linear order is fixed by that, and then. So this is essentially it. This is all that I wanted to say. Let me just come back to that situation. So what do you prove Ramsey really for? You actually look, instead of looking at S2, you look at this bijection with the linear order. And then, so what structure do you get? So back to Ramsey. Back to Ramsey. So you look at this set here. So I will draw it as a line. So what is it? It's really, the endpoints are not in. So this is really Q. And then this Q is divided into 2 subsets, namely P0 star and the inverse of P1 star. These 2 subsets partition Q, and they are both dense. So it's Q with a partition, let's say this, Q, look at Q with linear order and a partition into two subsets, both of which are dense. That's your structure. You prove Ramsey for each of that. So this is for finite linear orders that are partitioned into two sets. And then, okay, so this takes some work, but this can be found in the literature. So, and if you, a moment of thought tells you that if you prove Ramsey for that, you will have Ramsey for the age of S2 star, yeah, by this bijection. So it's not difficult to check. This takes a little bit of work, right? So, but this situation is more, you can look it up, for example, in the KPT paper. Yeah, so again, for Ramsey, you go back to some kind of order. Yeah, so this order is kind of almost there, but it's not quite the right thing. So this is kind of nice, this example, like that. So, okay, so I think I wanted to do one more. So I stated, and I don't, so just, I think just to do something else, we'll note, so I stated this Andy Zucker's theorem that says that if I have a Fryset structure F, its automorphism group is, its automorphism group has the universal minimal flow, is the universal minimal flow of the automorphism group is second countable, if and only if each element of age of F of the structure has finite Ramsey degree. So we knew what finite Ramsey degree was. And then we could, I mean, let me maybe not go into it because I want to introduce this other stuff, but at this point, we all have all the tools to show, actually the last proof that we did, to show that if odd of F, yes, so I'm talking without writing anything, so here Zucker's thing is that F Fryset odd of F M, let me write this, second countable, if and only if each structure in H of F has finite Ramsey degree. In H of F. So at this point, we could prove this direction. The reason is we completely analyzed that situation. So we know what this thing is. So if M of odd, if it's second countable from this analysis long time ago, it's odd of F divided by odd of F star completion, appropriate completion, where F star is this expansion by relations, yeah. But then these two, this odd of F divided by odd of F star, it's isomorphic by it's not by Lipschitz, but by uniformly continuous equivariant map with X star, if you remember, with X star. And then we knew that if with X star, so for this X star would have to be the universal minimal flow. And last time we proved that if X star is the universal minimal flow, then each structure was part of the proof. It was the first half of the proof. Then each structure in H of F has finite Ramsey degree. So this we actually essentially is already in what we proved. Going back takes some work, right? But so I will not do it. You can go and you can check Andy's paper in the transactions. And so I think this is all I want to say. We could have done, I mean, we counted it very carefully last time. So we still have 4 meetings because 4 is 5 minus 1. And we counted it to 5. So we still have enough, we'll have enough time for that. But I thought I would do this, you can look up, and I would do a little something different. Yeah. And then, okay, so that's it about topological dynamics and connections with KPT and all that. So I was thinking, so what's left is either it is measurable dynamics or some descriptive dynamics. And I thought maybe I will do some descriptive dynamics. Maybe we'll get some connections, little connections with measurable dynamics at the end. So there is a nice theorem I want to talk about. Unless people object, if people object, then let me know. Not now, but we can Because there is a way of, I want to prove one theorem, and there is a way actually after that theorem to go sideways, but and stay coherent, and stay coherent. So the theorem I want to talk about is a very nice result of Becker and Kekris. So let's now descriptive dynamics. Descriptive dynamics. So, okay. So a nice theory. So we have, there were two, if you remember in the beginning, we talked about this context. And there were two kind of categories there. There was, so G, a Polish group now. So G can act on X. This is maybe X standard Borel. Standard, not Borel. So I only remember, this is, I just remember the it's X equipped with a sigma algebra, but it's not just any sigma algebra, it's a sigma algebra of Borel sets of some Polish topology. But there is no direct interaction between G and the topology on X. G only sees the Borel sigma algebra, right? So this action here is, the action is a Borel action, the Borel action. Right? So to be completely precise, the action or an action is a function from a product to X. This function as a function of two variables is Borel. This means on G, I have a Polish topology. It's a Polish group. So it has a sigma algebra. Here is a sigma algebra. I take the product sigma algebra. So the sigma algebra generated by rectangles. And with respect to that product sigma algebra, this is a Borel map. That was the first. So both of these are natural context for descriptive dynamics. And two, I have again an action, X, a Polish space. And then, of course, naturally here, I would say the action is continuous. Again, as a function of two variables, it's not. Yeah. So there are these two contexts. And clearly, of course, if I'm here, I can forget some of the structure and get here. Yeah? I just forget, take the X, take the sigma algebra generated by the Polish topology, and I am here. Okay, but now, so there is this theorem of Becker and Kekris that says that actually you can also go the other way. It's a theorem. It's a kind of interesting in the broader picture, but it also is applied. It's actually applied. So theorem Becker-Kekris, and the theorem is that let G X standard Borel be a Borel action. Okay, then let's something. Then okay, there is a Polish topology here on X that gives you the Borel structure. But what the theorem says, there is a Polish topology on X that gives you the Borel structure and makes the action continuous. So it puts you in this richer or more rigid category. Then there is a Polish topology. Tau on X such that tau generates, or Borel of tau, Borel sets of tau is equal to the Borel structure on X, and two, maybe A and B, the action is continuous with respect to tau. Yeah, so I can go the other way. So we have to. Okay, so hopefully people see that's a non-trivial statement, right? If you just take a topology, you have to manufacture it for the action. You cannot just take a topology. It won't be, the action has no chance of being continuous. All right. So I want to talk a little bit about just the background from descriptive set theory. How do we get this? The statement has some nice, this is a little bit nice tools that are used in it. Something called Vought transform has this nice interaction between Borel sets and Berg category or Meager sets, and has some nice kind of uses nice preservation properties of Polish topology. So one thing one should, so maybe some background, and I'm not sure, I don't remember now if I stated those, but so there is a theorem that so it says the following thing: let tau n in n be Polish topologies on set X such that all of them refine Hausdorff topology. Hausdorff topology. So the way it's used normally, and this is how we will use, they are just increasing. Tau 0, tau 1 is stronger than tau 2, tau 2 is stronger than tau 1, and so forth. So all of them refine tau 0, and tau 0 is Polish, so it's Hausdorff. Then the topology and generated by the union over n tau n is Polish. So as you increase the topologies, you can take the supremum, and that's it's a nice. It's good to know this in the abstract like that. The proof is quite easy, right? Because what do we have? We take so let's make this maybe script t. Let's make it into script t, and notice there is an embedding x script t. You embed it in the product over n x tau n. There is a diagonal embedding. So you take the point x and you map it to x, 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 and so forth. Okay. And then what you notice is the important thing is that the product is continuous. The product is continuous. That's lack of coffee, I think. The product, so it's easy to check that the product of Polish topologies, so notice the product X of Polish spaces. This is a Polish space with the product topology. Of course, you take it with the product, topology. It's a Polish space. This embedding, this maybe I will call it something F. F is clearly is 1-to-1. F, the image of F, f of x, is closed in as a diagonal should be x tau n, and F is a homeo onto the image. So that does it, because the product is a Polish space. Actually, well, I wrote one-to-one here. Let me erase that. F is a homeomorphism onto a closed subset of a Polish space. So if you have a Polish space, closed subsets are clearly Polish, just to restrict the metric. But and then you have to check that this is homeo. Okay, so that does it. So now a puzzle for people. So I assume there that they all refine this Hausdorff topology. The question is, where is this used? It's the diagonal is closed. Very good. Yes. So this is where it is. So they have. So you use it here. Hausdorff refinement of a fixed Hausdorff topology. Yeah, because there is really no connection. So this otherwise, these topologies, they don't have anything to do with each other. These tau n's, they live on the same set. This diagonal is kind of nicely written as a diagonal, but it's almost like an arbitrary subset there. But this Hausdorffness of the common the fact that they come, this is what connects them, and this is what makes the diagonal closed. Okay. So this is one thing. Another thing, this second thing, I'm sure I mentioned. And I will just mention it again. So this is one, maybe I will write it as a theorem also. I'm not sure I proved this though, but okay, this can be, you can look it up. These are, so this I proved, it's not difficult to prove, but I will not do it. So the second thing is, let's say I have two Polish spaces. And we have to be careful with time. It's 45. Last time even they brought somebody from the administration to interview. So okay, XY is XY Polish spaces. B subset of X cross Y Borel. And then I want to look at the projections of, if I look at just the projection of B onto X, I'm in trouble. That's not Borel, right? This is the famous Lebesgue's mistake. So this is not Borel, but I can gently project it, right? So then the sets of all x's in X such that I will write it, and then because it will be convenient to use these quantifiers. There is many y in Y such that X, Y, and B, and the set of all X in X such that for almost all Y, X, Y, and B are Borel. So you prove, okay, so what are these quantifiers? First of all, this just says this, what this says is that there is non-meager the set of all Y such that X, Y, and B non-meager. And this says that the set of all Y such that X, Y, and B is comeager. I might have introduced this notation. This is a very convenient notation. Yeah, so these are Borel sets. This is proved by transfinite induction on the complexity of B, right? This is you start with open sets and then you do it. Okay. So I will not prove that. So this is fine. And let me introduce I think we have all the background. So this can be found in, for example, in Kekris's book or Srivastava's book. Okay, and then I want to talk, there is another tool that will come up a lot, and this is called the Vought transform. So the Vought transform. What transform? Okay, so what do we have? We have an action. So background assumptions. There is an action of G onto X, and then there's, I will just write A star, A subset of X, and then A star is all the points in X that most elements of G move to X. Yeah. So this is the set of all X in X such that for most points in G, Gx is in A. Yeah. So for this to make sense, really, this is, I mean, the definitions are completely general for a general topological group. The topology on G only will matter. Really, it's for Polish groups, right? So here, G Polish. Yeah. And then X, again, this is arbitrary. The action can be arbitrary. X can be just a set. But the context that we'll be applying it to, it will be a Borel action. X will be a standard Borel space. This makes it, if you look at it, I mean, you want these sets decent. So you want, like, when A is Borel, A star should be Borel. So if there's, the action is not Borel, you are in trouble. This is the set of all X in X such that there is a substantial number of elements in G, Gx in A. Yeah. So again, let's look at it. So there is some. So here is G. Okay. G acting on X. So I have G here, and there is an X, and there is a set. A set A subset of X, and I want to look at all the points. If I look at a point and I ask, does it qualify to be here? Well, what must happen, most elements of G, some of them may miss A, but most of them have to put it in A. And this one, a substantial number has to put them in A. And we note that if A, so if the action is Borel, so if X standard Borel and the action is Borel and A is Borel, then so are A star and A triangle. Yeah. And the reason for it, it's immediate from there, right? What are you looking for here? Notice in that situation, you are looking at the set of all pairs XG such that Gx in A. In both situations, we are looking at this subset of X cross G. So if the action is Borel and A is Borel, this is a Borel subset of X cross G. And then here, I'm looking at the second set with X equal to X and Y equal to G. I'm looking at the second set, and here I'm looking at the first set. So both of these are Borel from this general principle. So this is as explained above. Okay. And then, so I will just write these definitions because this is what, so this is nice to introduce them this way, but we'll actually use a local version of those. Star U is equal to the set of all X. Again, define the set of all X in X. This is the same definition. So for pedagogical reasons only, I put the other ones. And here, U subset of G open. That's how it's used for open subset. So the first one says, maybe not most points in G put X into A, but most points in U put X into A. This says a substantial number of points in U put X into A. Yeah. So that is local versions. And if you look at this argument for Borelness, nothing changes. Only this is now X G in U. So it's a subset of U X cross U. And then the same argument applies. But our argument is abstract, right? It doesn't depend on if there's a full group structure. So these are Borel again, Borel as in circumstance, in the above circumstances. Okay. So okay, let's finish because so let's finish here. And next time, so I think we have all the background that we need for the theorem. So we'll use these Bott transforms, we'll use that theorem, and then we'll manufacture, using these tools, we'll manufacture the topology. Okay, so this is it for today. Thanks.